Hi, my name is Tim and I'll be presenting our work titled Cross-View Online Clustering for Dense Visual Representation Learning. This is joint work with Thomas, Bezat, Tina, and Jean-Philippe. The goal of self-supervised visual representation learning is to learn general representations of images that can then be transferred to any downstream tasks. Most works aim to learn representations at the image level by training it to be invariant to standard data augmentations. That works pretty well when you're interested in image-level downstream tasks like classification, for instance. When focusing on denser downstream tasks, it makes sense to apply the self-supervision at a more granular level. So instead of applying a coherence loss at the image level, we apply it at the object level. This is particularly well motivated on scene-centric datasets where different objects can be present in different views. CrOC efficiently figures out where the objects are and matches them cross-view to apply coherence. So this is an overview of the presentation. First, we'll have a recap of what image-level self-distillation is. Then we'll move on to the main part of the paper, which is object-level self-distillation. And then finally, we will discuss some results of our method. So first up, image-level self-distillation. Let's first discuss some notations so that we can have a look at equations. X tilde1 denotes an augmented view and F denotes an encoder. When we feed the image to the encoder, we get a dense representation, which is an n by d representation, where n stands for the number of spatial locations in the representation and d is the dimensionality. So once you have this dense representation, you can compute an image level representation by averaging this dense representation over all spatial locations. So for instance, in a VIT, this would be using a self-attention layer, or in other networks, this can be, for instance, a simple global average pooling. So self-distillation applies two different data augmentations to an input image X from your dataset to get two views, X tilde1 and X tilde2. These two views are then fed to two different encoders to obtain two dense representations and two image-level representations. So in image-level self-distillation, the dense representations are completely discarded and only a single loss is enforced between the two global representations or image-level representations. The loss here, which is illustrated, is a loss coming from Dino, where the two global representations are fed to two different heads, which map the global representations to probability distributions, and the loss that is enforced is the cross entropy between the two output distributions. Here we have the loss in more detail. In particular, the loss is made symmetric by feeding both X tilde1 and X tilde2 to the two branches and then averaging the loss that is obtained. This is called self-distillation because one branch is actually a slow-moving average of the other branch. The slow-moving average is called the teacher branch, and the online branch is called the student branch. Gradient updates are only taken with regards to the student branch. So that was it for image-level distillation. Let's now move on to object-level self-distillation. Instead of self-distilling image-level representations cross-view, we would now like to do the exact same thing but for object representations. So in order to do this, we need object representations in each view, but also now we would need to know which object representation from view 1 is mapped to which object representation from view number 2. Multiple approaches have been used by prior works to localize objects in the image. These can be split into methods that work in the joint space of the two views or methods that work in the intersection space. Another axis of comparison is whether the clustering/matching is done offline or online. On the left, we have methods that work in the union space and use offline clustering. This is mainly done using pre-trained segmentation networks on the original input image. On the right, we have methods that match objects from one view to the other, but only in the intersection space of the two views. This can be wasteful, as the views can have very little overlap sometimes. And in the center, we have our method CrOC, which works both in the joint space and using a matching/clustering algorithm, which is purely online. Let's get into the meat of our method CrOC. Let's first assume we have a clustering oracle C which assigns tokens to clusters. We use this oracle to cluster the joint view, which we denote by zcat. It is a 2n by d matrix. The output assignment that we get is 2n by k, where element ij denotes a soft assignment of token I to cluster j. Given this assignment, we can split it view-wise to obtain the assignments q1 and q2. Note that the clustering in the joint space and splitting the assignment view-wise gives us free cross-view matching. Given our assignment q1 and q2, we can produce object representations by pooling the representations assigned to each cluster k. These object-level representations are stored in a matrix which we denote by C. The object-level self-distillation loss is completely analogous to the image-level self-distillation, with the exception that we have multiple object-level representations per view instead of a single image-level representation. The self-distillation loss is averaged for every pair of object-level representation assigned to the same cluster. Here is an overview of our method CrOC. It is divided into three parts: join, locate, and split. In the join part, n tokens from each view are merged into two n tokens. In the locate part, these two n tokens are clustered to k clusters. And in the split part, the clusters are split view-wise to compute object-level representations in each view, which are then later self-distilled pairwise. Let's uncover the clustering algorithm used. It is based on an optimal transport formulation using the Sinkhorn-Knopp algorithm. This algorithm is chosen because it is fast and solves a constraint optimization, which helps to avoid collapse issues. The cost of assigning a token to cluster K is proportional to its similarity. On top of this, we add a positional prior to favor compact clusters. The total transport cost is the sum of the semantic cost and the positional cost. The Sinkhorn-Knopp algorithm then finds an assignment Q, which is the least aligned with the total cost and which satisfies the constraint on the marginals. So now let's have a look at some results. Here are some visualizations. On the left, the two views are shown, and on the right, the object masks are shown. Note that these are online clusters with which the object-level self-distillation is enforced, not a result of a downstream segmentation. On downstream linear segmentation, we see that CrOC is comparable with previous methods while being trained only on COCO. When trained on ImageNet, it outperforms previous works. In conclusion, we propose a novel online centroid level self-distillation algorithm which we call CrOC. CrOC is online, fast, and obtains excellent performance on dense downstream tasks. Thanks for listening, and please come have a chat at the poster.